Okay, so today we'll be looking at the part 2 of the law of distance absorption of gamma or beta rays. So we've already done the part 1. If you haven't seen that one, check through the videos on the channel and then you see that one, how the experiment is performed. Okay, so let's go straight to how the table will look like. Okay, in the experiment we're only interested in two things. So if you watch the part 1 of the video, you realize that we are interested in two things. One, the radiation intensity, and then two, the thickness of the absorber, which is the D in centimeters. Normally we'll use the vernier caliper to measure the thickness, which gives us the unit in mm. Okay, but we have to convert it to cm. So we have about 5 absorbers. We have iron, we have aluminium, lead, plexiglass, and then concrete. Okay, so this is how the table will look like. We have only two parameters, or only two quantities, which is the intensity and then the thickness. Now I didn't write the unit for this because it depends. Radiation intensity, it can be measured in sievert. Okay, sievert. Also, if somebody writes Curie, right? If somebody writes this word from Marie Curie, is not wrong. Okay, so that's another unit. So either sievert or Curie. Okay, so that's the unit for the radiation intensity, I. So all the I have those units. So that's why I didn't write it. Okay, so this is the equation that we are looking at, or we'll be making use of in this experiment. This is the equation. Okay, we'll look at the explanation of this equation and then how we can use it to solve our radiation intensity. Now for this experiment, we are interested in about 3 things: the half-life thickness of the absorbers, the absorption coefficient, and then the attenuation, mass attenuation coefficient. Okay, now the mass attenuation coefficient is the absorption coefficient over the density of the material. So we'll look at that. So this is how the graph is supposed to look like. Okay, depending on what you are plotting, right? If you are plotting I against D, it will still look like this. If we are plotting I naught against D, it will also still look like this. Okay, now this experiment is also known as the inverse square law. Okay, we'll be making use of cobalt 60 with atomic number of 27. Okay, at the excited stage, right, cobalt 60 would disintegrate into a beta particle, and then at the ground state it gives us 2 alpha particles, right? It will further disintegrate into gamma particles. So at the excited state it disintegrates into beta, and then at the ground state it further disintegrates into gamma particles or gamma radiation. Okay, now there's a little definition of the inverse square law, right? The inverse square law, it tells us that the impulse rate I per area around the point source decreases in the inverse proportion to the square of the distance provided the gamma quanta can be spread out in a straight lines and not deflected from the tract by interactions. Okay, so there's a little equation surrounding the inverse square law. You can have a look at it later on. So there's a diagram representing the inverse square law. Okay, so that's the point source and then the area, and then it increases by the distance. Okay, so this distance depends on the energy of the quanta. Okay, the distance depends on the energy of the quanta. Earlier on I said that the beta particle, the cobalt 60 disintegrates into beta particles at the ground state, and then further at the excited state, and then further disintegrates into the gamma particles at the ground state. Okay, now for absorption to happen, or for absorption to take place, it depends on 3 effects. Okay, 3 effects. 1 is the Compton effect, 2 photoelectric effect, and then 3 the pair formation. So for absorption of gamma rays to happen, it depends on these three things. Okay, the Compton effect, photoelectric effect, and then pair formation. Okay, so as I was saying, the absorption coefficient of the absorber material depends on the energy of the gamma quantum. Okay, so as I said, we'll be finding three things: the half-life thickness of the material, okay, which is defined as the thickness at which the impulse counting rate is reduced by half. So the half-life thickness, right? The half-life thickness of the material is defined as the thickness at which the impulse counting rate is reduced by half. And then this is the formula for finding our attenuation coefficient. And then this is our absorption coefficient, which we will find from the graph after plotting the values in the table. Okay, so how to find? First of all, after getting these values here, right? After getting these values here, we are plotting the lane of this. So the table is this and this, but we are plotting lane of this. So there should be another column for lane I, right? So there should be other columns for lane I. So it should be I, D, and lane I, D, and lane I for all the absorbers. And then we'll have a graph like this. Now, since we are having about 5 absorbers, okay, there's no need for us to separate the graph. Okay, we can just draw all the lines on one graph. So we can just make this, let's say, we can call this Fe, iron. We call this Al, aluminium. We can call this Pb, lead. And then the others, we add all of them on one graph. Okay, then after that, we find the slope for each. Okay, we find slope for each line, for all the lines. Then after finding the slope for each line, we come and use it in the equation that we are given. Okay, now first of all, we are plotting the lane of this against this. Okay, so we need to apply log identity to it. Then when we do that, we'll come and get this particular expression here, right? We can call this expression equation 2, and then we call this one equation 3. Okay, then when we make lane I the subject, because we are interested in plotting I, we are interested in plotting I against D. So after applying log identity to this, we make this, we have to solve for lane I. Okay, and then since we do that, we will come and have an expression like this. We call this equation 3. Now we realize that when we are supposed to compare this to the equation of a straight line, indeed we are interested in finding a straight line. We'll have this as our y component, we'll have -1, and then this absorption coefficient as our slope, right? So this becomes our slope, this becomes our x component, and then our lane I naught becomes our intercept. So after finding the slope for each line, we'll come and equate the value of the slope to this, right? We equate the value of the slope to this, and then we can find the absorption coefficient for all the materials. Okay, for all the absorbers or the materials. Now we say that the absorption coefficient is the amount of radiation a material can absorb. Okay, so that's how we find the absorption coefficient after plotting your graph, right? From this expression here, equation 3, we can call this equation 3. Okay, so now we have about 3 aim or task. First one, absorption coefficient. The second one is the half-life thickness of the material, and then the third one, mass attenuation coefficient. Okay, we are done with how to find the absorption coefficient, which will also lead us to how to find the half-life thickness of the material, and then to know that we need to further apply log to this expression here. Okay, we need to further apply log to this expression here. Okay, so Now, to find the half-life thickness of the material, we further apply log to this, right? This expression here. This expression. We further apply log to this or this. This and this are the same. It's just the arrangement. So we can choose to apply log to this, right? And then when we do that, we'll get this expression here. We'll come and get this expression here, okay? Now, if we are considering the half-life, the intensity is 1/2 of the intensity knots, which is in the video, the first video, we said that this is the intensity when there is an absorber, and then this is the intensity when there is no absorber, okay? Meaning that this is half of this, right? Intensity is half of the intensity knot, which gives us the reduced ratio. So because of that, it makes our D also goes to half, right? Our D, which is the half-life intensity, half-life of the material, goes to half, which leaves us to an expression like this. This leads us to an expression like this. Now, further applying log to it, our ln 1, right, from this expression here, our ln 1 goes to 0, and then we'll be left with this expression, which is this. We'll be left with this expression, which is this, because our ln 1 goes to 0, and then this will be left, this expression will be left here. And then with that, making D on half the subject, it gives us ln 2 on the absorption coefficient. You get it? So this is how we find the half value thickness of the absorber material. Okay, when we make from this expression, we can call this expression, we can call this 6, equation 6. Making equation 6 the subject, D the subject in equation 6, we'll get an expression like this, and then this will help us to find the half value thickness of the absorber material. Now, mind you, we've already found for the absorption coefficient for all the materials already. So if you take aluminium, so you can just write that D half of aluminium ion equals to this ln 2 on the mu for the absorption coefficient for ion. So you do for each material, right? You do this for each material, so you find the half life value for each material. Okay, half life thickness value for each material. So that's how you find the half-life thickness value, okay, for all the materials. Now we have this, so we can further go and then find the mass attenuation coefficient. Okay, now we say that the formula for finding the mass attenuation coefficient is given by this, our absorption coefficient on the density. Now the density of the materials will be given to you, okay, the density of the materials will be given to you. If it's not given, you can just check it on the net, and then you find the density of aluminium, iron, concrete, glass, and then lead. So you substitute them here, and then use the absorption coefficients for each material on top here, okay, to find the mass attenuation coefficient. Now, the mass attenuation coefficient is how easily a mass of a material can be penetrated by a beam of light, sound, particles, or other energy or matter. In this case, we are using radiation from cobalt 60 isotope. Okay, so we are finding how easily a mass of a material can be penetrated. So these absorbers that we are using, how easily they can be penetrated by the cobalt material. Okay, so that's how we find our absorption coefficient, our attenuation coefficient, mass attenuation coefficient, and then half-life thickness value of the materials.